Hi there, welcome to this lecture series on matrix algebra. This is lecture 34. The topic is singular value decomposition, and the second lecture on the topic, and this is part 2 of the lecture. So in part 1 we reviewed the theorem of singular value decomposition, and we had an example, and in this part 2 we'll be talking about applications. In particular, the application in image data compression. So we'll pick up at the end point of the theorem of singular value decomposition, and that is, we realize that the matrix A can be recovered as the sum of all these terms. So here, let's say A is an m by m matrix, and then it has a bunch of singular values, sigma 1, sigma 2 to sigma q, and we line them up, and from the largest one and going down, and they are all non-negative. And A can be written as the sum over k of sigma k, uk, and vk transpose. Now here we make an important assumption, and which we will justify later. So assume that among all the singular values here, and we see that if I take the first few, they are much bigger than the rest. So if the value sigma from q plus 1 and on to the last one, they are non-negative, they're non-zero, but they are very small. Then each term here with the k from q plus 1 to p will be multiplied by a very small number. So we can drop them if they are so small, they're not significant. In other words, we can approximate A by only taking the first q terms, small number q, and then the same expression here. So we have an approximate sign. So this would be very important in image data compression. Let's say you have an image, a rectangular image, and it's stored in a matrix A. Let's say it's 1000 times 1000. Or in reality, it could be much bigger, but let's just say 1000 represents a pretty big number. So we make the assumption that the singular values of this A matrix, let's say, start from 20, sigma 20, 1, 22 to 1000, are very small. Then we have the idea. So instead of computing the full singular value decomposition, that A is the sum of all these, where you are summing over 1000 terms, we can only sum 20 terms because all these are small. So we can approximate A with the k from 1 to 20 of this expression. And then if that gives us a very good approximation, and that's good, we kind of more or less have the A matrix at a much lower storage memory cost, because you need to store much less information. Let's do a computation of how many numbers need to be stored. Okay, storing the entire matrix A would require 1000 times 1000, which means 1,000,000 numbers. And then how much do we need to store this approximate singular value decomposition? Let's call it A SVD. Well, that we just need 3 sets of informations. So 20 singular values, that's 20 numbers, and then we need 20 left singular vector UK, which is each UK is a vector of length 1000, so this will be 20 times 1000. And then we need 20 right singular vector vk, which is also a vector of length 1000. Okay, so we can add up. So you will need 20 times 1 here is the number, and 1000 here is the length of the vector, and 1000 is the length of the vector. And then you calculate that, you see you need about 40,000 numbers. So comparing 40,000 to 1 million, this is much less. Now here we put in a very important remark, which involves very deep mathematics. Okay, so for most images, if the A is a matrix representing a square-shaped image, and one observe and one can also show that the singular values, if you sort them out from the largest one going down to the small one, they would decay very fast. Decay means as the index gets bigger, the value gets smaller. So for some rather small q, here we would have the sigma q here is already very small, and then the remaining ones is even smaller. So this is particularly true for images with structures. So there are websites that demonstrate how the singular value decomposition to decompress the image data, how it works and what happened to the singular values, and how plots of how it decays. I encourage you to go visit them and have fun. Let's take an example of an image. So just want to mention that this is a image taken from a textbook written by me, an introduction to numerical computation, published by World Scientific in 2020. And the image is my former cat, and she is a black and gray tabby with stripes and patterns. Okay, so let's look at the detail of what we do. So this picture now is stored in a grayscale image, and the size of the matrix is 638 times 640. And here on the left here is the original picture. So the required storage will be 600 times 600, is about 400,000 numbers. This center image here, one can see that it's a cat, and you can recognize some features of this cat and how she looks like, but it's a bit blurry. So in this one, we approximate the singular value decomposition by using only the first 20 singular values. And then we can calculate the required storage. That will be 20 times 1 plus 600 plus 600. So it's a bit over 25,000 numbers. So comparing to 400, it's very small. And now this image on the right here, we can see is much sharper. And in fact, if I compare this to the original picture of the cat, we can barely see much difference. It looks almost the same, as good. So here is an approximation where we use the first 60 singular values. And then we can calculate the storage. It will be 60 times summing of these, and it will be about 76,000 numbers. So still is much less than 400,000 numbers. Now let's have some spin-off discussion. Since we carried out diagonalization of matrices of different types, let's make a comparison. So if A is a square matrix, and then what we do will be we would seek an invertible matrix P such that P inverse A times P is a diagonal matrix. And this is achieved by taking this matrix P as the collection of all the eigenvectors, and v1, v2, vn, and they are linearly independent eigenvectors of A. And then if A is a general n by n matrix, and then we would be seeking two orthogonal matrices, capital U and capital V, such that U transpose times A times V is a diagonal matrix. And this is achieved by taking this V here is a collection of vectors v1, v2, vn. They will be the eigenvectors of A transpose times A, which is symmetric. So this forms an orthonormal basis of Rn. So all the vectors here, vi, they will have length 1, and they are perpendicular to each other. So I just want to put them side by side so we see the difference in these two procedures. Let's now take a look at relations between eigenvalues and singular values. For square matrix, let's take an example. A here is a square matrix, and we can find the eigenvalue of it. This is a procedure we are very familiar with. Form the characteristic polynomial and find the roots. So we have 3 and -2. And now we want to compute the singular values. So we need to compute the matrix A transpose times A. Let's call it B. We work out this product and we get this symmetric matrix. And we can carry out the computation of the eigenvalues for this matrix, and then we see that we get these numbers because it's not an integer anymore. It involves square root of 10. And then the singular value would be the square root of the eigenvalues of this matrix B. So singular value would be square root of 7 plus square root of 10, which is approximately 3.18. And the singular value of the second one is the one taking the minus sign here. And then if you work out, is about 1.9. Okay. So I would say that in this case, the singular value and the eigenvalue, we don't see any clear relationships between them. So what about a symmetric matrix A? Let's take a symmetric matrix A, and let's say it looks like this. So let's find its eigenvalue. Okay, we carry out the computation of the characteristic polynomial, and that's what we get. And then we find the eigenvalues, and we found one is 3 and one is -2. And now we compute the singular value. So we need to compute the B matrix, which is A transpose times A, which is just A squared because A is symmetrical. And then we have this matrix, if you work out. And then we want to find the characteristic polynomial to compute the eigenvalue. Let's say Q of mu, and that's what you get. And then eigenvalues of B, then we'll have two of them. Mu1 will be 9 and mu2 will be 4. So now we can find the singular values of A, which will be the square root of the eigenvalues of B. So sigma 1 would be square root of mu1, which we see is the absolute value of lambda 1, which is 3. And then sigma 2 will be the square root of mu2, which is the absolute value of lambda 2 equals 2. So here we see that for a symmetric matrix, the singular values are the absolute values of the eigenvalues of the matrix A. So one want to ask the question, is this a general property or just a coincidence of this example? Now let's recall what we know about eigenvalues. So we know that if you have A, which is an m by n matrix with eigenvalues, lambda 1 to lambda 2 to lambda n, and eigenvectors v1, v2, vn, then we know that A square will have the eigenvalue which will be just lambda 1 square all the way to lambda n square, and with the same eigenvector. And then in the case where A is a n by n symmetric matrix with eigenvalues lambda 1 to lambda n, then we will have the following. So A transpose times A would be just A square, and then it will have eigenvalue lambda 1 square to lambda n square. And then the singular values of A are computed as sigma 1 will be square root of lambda 1 square, which is absolute value of lambda 1. And so on and so forth to even the last one. Sigma n will be the absolute value of lambda n. And in a even more particular situation where A is positive semi-definite, that is, the eigenvalues are non-negative, then the singular values are the same as the eigenvalues. So as a final discussion, we will talk about rank 1 matrices. So assuming A now is an n by n matrix, we know from our singular value decomposition theorem, A can be written as the sum of all these matrices. So what are these matrices? So we see that each matrix is the product of two vectors. This is a column vector and this is a row vector. So this is a column, this is a row. So if you have a n by n matrix formed by the product of two vectors like this, then we know this matrix has rank 1. Let's look at it. So let U be U1, U2 to UM, and let V be V1, V2, Vn, and this is V transposed. Then this product gives you this n by n matrix, and with each entrant will be U1 times V1 and U2 times U1 times V2 and U2 times Vn, and so on and so forth. So if we look at all the row vectors, then we see that all of them are scalar multiples of V. So this is the V vector multiplied by U1, and this is the V vector multiplied by U2, and so on and so forth. And therefore, the matrix has rank 1. And then, what is the A matrix? A here is the sum of all of these, and all the way to P. There are P of these matrices of rank 1 that you add up. And then, as a result, this A matrix will have at most rank P. The rank cannot be bigger than P. So that is the end of this lecture, and next time we will change topic. We will look at linear ordinary differential equations and applications of what we have learned in matrix algebra into that to find proper solutions and discuss properties. Okay, so I hope you enjoyed this lecture, and I'll see you next time.